Thanks very much. And I want to start by saying when Subhadeep invited me to present here, my first response was, I haven't made a precision measurement in 20 years. Why am I being invited? And of course, it's because it's a broad conference about many things. In fact, the only thing I ever measured precisely was the von Klitzing constant, the quantum Hall system, and that was to a measly 5 digits, which is laughable. So with that, I'll tell you a little bit more. But first, remember that you students should be asking questions. And my experience is the best questions are an inverse function of age. So the younger you are, more likely than not, the better your question is going to be. Okay? So I really encourage questions. In fact, I'm going to almost demand interactivity. Lastly, the previous talk reminded me of this super awesome comic. So just imagine it applied to LIGO instead of the LHC. So I don't know how many of you have assembled IKEA furniture before, but obviously this is not how it works. Okay, so with that, I'm good to turn this off. Well, that goes up. I'll start over here. So the working title of my talk is this. And the first thing I like to say is that almost nowhere is there such a thing as precision analog simulation of any kind, because that's why the whole concept was given up in the electronic era as things diverge rapidly. So what can we hope for? We can hope for accurate quantum analog simulation. And what I mean by that is that we can attempt to realize certain Hamiltonians or open quantum systems, and provided that we have sufficient control over the mistakes we've made in their realization, we can accurately simulate them, and the outcomes will then be precise to our measurement capabilities. My background is ultra-cold neutral atoms, sometimes with, sometimes without optical lattices. And generally speaking, in this field, our accuracy is at the level of 1 to 10%. And our precision is typically comparable to that. And one point I want to make right at the beginning is I'm not using my lack of precision as an excuse to say, actually, I'm inaccurate. There are very good reasons why we actually cannot accurately realize the Hamiltonians that we do. So let me give an example of that. Probably many of you have heard of the Bose-Hubbard Hamiltonian. How many have not heard of the Bose-Hubbard Hamiltonian? All right, so 20%. So the Bose-Hubbard Hamiltonian is a description of bosonic particles hopping in a lattice potential. And they can do two things. They can move around, or they can interact with each other. And the Hamiltonian for that is this. I'll do it in one dimension. So for those of you maybe who haven't done a quantum field theory or many-body physics class, real quick, what this notation is saying is there's a strength of hopping, which I use J. I have a creation and annihilation operator that puts particles into site J, for example. So this says I'm moving a particle from site J to J plus 1, and the Hermitian conjugate takes it back. And then I have a second term which says particles interact. N is a number operator, which is no more than A dagger J, AJ. So this counts the number of particles in the site. So what you see is if there's 0 particles in the site, no interaction energy. If there's 1 particle in a site, there's no interaction energy. But if there's 2 or more, you have a quadratically increasing interaction energy. And that's it. That's a Bose-Hubbard Hamiltonian. And if you've ever read something about cold atoms and optical lattices, this is sort of like what really kicked off the connection between many-body physics and atoms and optical lattices. So the very famous paper from Manuel Bloch, was it 2002, maybe 2003, something like that, said they realized this Hamiltonian and saw the transition from a superfluid phase where tunneling dominates to an insulating phase where interaction dominates. And I'm here to tell you that this is an exaggeration of reality, that we do not realize this Hamiltonian in the laboratory. We realize this Hamiltonian plus a whole bunch of other terms, which by and large are small, but they are not negligible. So as an example, can any of you think of another term that is present in real life? Okay, let me just move it up. Okay, so I'll try again. So this, like I'm compelling interactivity here. So can some of you, it can be a guess. There's no wrong answers because there's a huge number of terms. But can anyone guess just a term that's present in the laboratory that's not present in the simple model? I can stand here all day. What's that? Great. Yeah, so our experiment is an open quantum system. So the laser beams making this lattice, and we'll talk about that later on, it doesn't just make a lattice potential. Occasionally you throw photons into different directions and we interpret that as heating or decoherence. That's not in this model. Another thing that's not in this model might be tunneling of long range. That might be J1. There'd be another term, J2, sum over J, that I think you can already guess it, moves a particle by distance 2. In fact, there's tunneling of infinite range in this model. And in the superfluid regime, actually, this tunneling is not negligible to the 10% level. Okay? It happens that it doesn't influence the phenomena of superfluidity very much. But in fact, it's a significant perturbation to the Hamiltonian. Okay? So when I say that our simulations are not precision measurements and they have inaccuracies, this is the inaccuracy I'm talking about. We are not even quantum simulating the Hamiltonian that we wish to be. But in the language of many-body physics, we typically are in the right phase of matter. So renormalization group says we flow to the same phases that the Hamiltonian typically has. Okay, but that's not an accurate simulation of the Hamiltonian. My goal for today is to give you guys a sense of where these kind of inaccuracies come in, so that if you get interested in any kind of quantum analog simulation, you will have the sort of sense, either as theorists or experimentalists, to say, well, how much of this problem do you need to look at in order to really be confident that your physical reality is going to be somewhat accurately modeling the ideal system you're trying to model. Right, so that's going to be our goal for today. Quick check. I'm going to be giving 2 lectures. The first one is going to be predominantly Blackboard to give you sort of this hands-on sense of how we might have an example of this kind of inaccuracy. And then tomorrow, I'm going to give more like the PowerPoint presentations that others have been given, using specific example from my own research, where I do the opposite of what I regularly do in a talk and try to call out all the places where we are being inaccurate, so that you can see what makes these experiments both good quantum simulators and also less than good quantum simulators. So my outline then is going to be F0, which is, I'm going to call the first one black box. Make sure I don't skip any bullet points here. So I'm going to talk a little bit about black boxes, and then I'm going to give an example of how we can realize something from condensed matter spin-orbit coupling, which is in fact not exactly the same as the spin-orbit coupling that atomic physicists usually talk about, that literally couples spin and orbital motion. And then I'm going to tomorrow give an example of how this plays out in the lab. Okay. All right. So what do we mean by black box? What I mean is that these quantum simulators attempt to operate in some piece of parameter space. They have parameter 1, parameter 2, where your simulation is valid. Okay. And parameter space can be big, and the validity range to your level of accuracy is going to be some subset of all parameter regimes. So I want to give a specific example of this right now, that if you've ever read a paper on cold atom physics, has been implicitly assumed whether you knew it or not. So that is, how many people haven't read at least one paper about ultra cold atoms? Great. So in that paper, if there were interactions present, what was the nature of the interactions? I'm not going to stand around and wait for this one too much because the hands came up. So mostly ultra cold atoms interact with very local interactions, and we like to claim that the interaction potential U is some kind of delta function. So we say that the atoms interact if they're sitting on top of each other, and they don't interact if they're not. And do you guys really believe that we have a delta function in the laboratory? Of course not. The interaction potential is actually more like a van der Waals potential in long range. So this is R1 minus R2, and this is some dimensionless energy with a hardcore center. That's for the S-wave interactions. If you're doing P-wave collision, there'll be some kind of barrier, and so forth for higher orders. Okay? So given that this is the true interaction potential, how can I possibly make this claim? Any contributions to that? Under what regime might this approximation be true? Okay, so aside from spurious resonances, there's two conditions. The first one is the energy of the input collision energy here needs to be small compared to the P-wave barrier. So if we're small compared to the P-wave barrier, you're not going to see the impact of P or higher order collisions. Secondly, this potential has a lowest bound state. If the energy of the incoming particle is much less than the binding energy here, then and only then can we approximate this collision as an S-wave phase shift, where the incoming wave comes out, experiences a phase shift, and is reflected outwards also in the same channel. Okay? And in that approximation, only one parameter describes the scattering, which is the S-wave scattering length, and then we can have this delta function approximation. So in that case, my parameter might be collision energy, and I would be saying that my simulations are going to be valid when my collision energy is less than or equal to, it turns out to be about 10 microkelvin. And I realized I was starting to shrink the writing, so I'll duplicate that. All right, so to add the confusion to this series of lectures, we have another energy unit. We had MeV, we've had Hertz, and I'll usually use Hertz, and now I'm using an energy unit. Our ultra-cold atoms typically are much colder than 10 microkelvin, so this approximation is typically valid, but not always valid. Another breakdown is what if it so happens that the last bound state in this P-wave channel is very close to resonance. Well, then you can resonantly couple to it and have modifications in this picture as well. So what this means is that in order to make this black box picture, you have to be relatively aware of a lot of atomic physics, all right? And if any of you are interested in doing quantum simulation problems in other platforms, be them superconductors, arrays of Rydberg atoms, or ions, each of these systems has its own nuances that you have to know at least something about in order to know when what you calculate or might be valid, or when you do an experiment that you're actually realizing the Hamiltonian features. All right. Okay, so I'm going to do part one now. But I'm doing bait and switch. We're not going to do that yet. So instead, I want to think about optical lattices. And probably how I start this is going to be something that you heard about in previous lectures, but that's okay. And I'm going to start at the very beginning. So I'm going to consider a two-level atom with one ground state and one excited state. And I'm going to illuminate it with monochromatic radiation with some frequency lowercase omega and a coupling strength omega. All right, so this is the next point of interactivity. Can you guys contribute the various terms in the Hamiltonian describing this two-level model? And let's furthermore make it simple. Say my zero of energy is the ground state energy. My excited state has energy E, ground excited. So can you guys tell me what this Hamiltonian is? Or even contribute a term? Okay, so let's good. Okay, so I'll make room for that. We'll add some more terms after that. Okay. What else do we have in this Hamiltonian? Okay, great. So I have all right, so I made the ground state zero energy, so I only have to write the projector onto the excited state. And now I want to investigate this term a little bit more. All right, so well, let's see, what do we need? We need a okay, I need to go from the ground state to the excited state and vice versa. But we've skipped a term here. And what have I skipped? What's that? Yeah, so the term I skipped, my drive term. Yeah, so I'm really starting at the beginning. We have an oscillating field. So this is the base two-level atom Hamiltonian. And in an earlier talk today, it was sort of flashed through that the process you find to solve this, or to generally solve it under most cases, is you make a transformation into a rotating frame, and then you make a rotating wave approximation. So is it familiar to any of you what the next step is going to be, the rotating frame transformation? So what we're trying to do is eliminate the time dependence of this coupling. So if you think from quantum mechanics class, everyone knows about the Schrodinger picture and the Heisenberg picture, and if you do quantum optics, you like the interaction picture. That's the one where the interaction, you take out the energy of the Hamiltonian, it's simple. But there's one more, and that's where you take out the time evolution here, or approximately. So the transformation we're going to make is going to be of a hold on, right. Unitary transformation. Okay, so what is that transformation going to do? It's going to say that, well, if you were in the excited state and you were uncoupled, your oscillation frequency would have been EGE over H bar. And we're going to take off some of that. And I'm telling you this because the graphical picture is very appealing. You imagine grabbing this picture and sliding it downwards by an amount equal to omega, giving this green state having moved down here. That's the picture we're going for. That's why we're doing this. And if this isn't coming back to you from having seen it before or having not seen it before, there's one more thing you need to keep in mind when you do this. So we imagine applying this U to this Hamiltonian. Well, this has two E's, it doesn't do anything. This E picks up a factor of E to the plus I omega t. This E picks up a factor of E to the minus I omega t. But this EGE is still here. So what have I not done? Yes, right. So what I didn't do is I should really think about this problem in totality. I have the usual time dependent equation. And what I'm going to do is insert identity and form to this unitary operator a bunch of times. So I just made a whole bunch of ones there. That's psi prime. H prime. That's psi prime again. And exactly as the comment said, I now need to act with this time derivative on this u. The action of that brings down a factor of I omega, which when all said and done ends up giving me a total effective Hamiltonian when I move the excess term from the left hand to the right hand side of this. And now I'm going to skip a step. What step did I skip? So I just made the rotating wave approximation. So the step I skipped is that when I act with this unitary on this Hamiltonian, each one of these things acquired an e to the, let's say, plus I omega t. I multiplied this plus I omega t by the minus I omega t in that cosine. That gave me a time-independent term and a factor of 2 from splitting the cosine into 2 exponential parts. But this plus e to the I omega t also multiplied the e to the plus I omega t term here. I threw that away. Throwing it away is the rotating wave approximation. And extra terms in real systems like Bloch-Stiegert shifts, for example, come from not ignoring that term. And in full generality, you can think about this in a more complicated Floquet picture that I'm not going to be talking about. All right, but you can sort of see already that we're throwing away terms. I just made an approximation. And even in the simplest possible atom, the 2-level atom, if you wanted to have a simple description like this, you had to throw away terms. Okay, so we have now sacrificed some accuracy. It's pretty normal to call this, oh, that green doesn't show up at all. Call this term call that term a detuning. How many people have looked or read a little bit or more about laser cooling? Good. I'm sure more hands would be raised if you were bolder. The sign of the way I've defined this detuning is sort of the natural way, but is the opposite of how it's defined in laser cooling, where blue detuning corresponds to plus with higher energy, and you'll see that's reversed here, okay, where the photon has higher energy. Okay, so just notice that in the notes I'm producing, I flipped the sign in the equations of what would be conventionally red detune versus blue detune. Okay. All right. Okay, so at this point, in order to make the rotating wave approximation, what has to be valid? Yeah, so I'm going to need that my coupling is relatively small. And I'm going to make it very small compared to little omega. Okay. So this is the thing that makes, if you want to think about in the Floquet picture, makes that whole sort of picture valid. So we're going to have that here. So then where I'm building towards is optical lattices. What have you guys heard about optical lattices? Like, how deep is the lattice? What's it proportional to? And what does it do? Yeah, so the optical lattice, we like to think about it as what? Sort of like in reference to the Bose-Hubbard examples. It's like a potential that atoms in the ground state experience, right? So you have this picture that if your photon is blue detuned, or red detuned, it fits in here, then someone will give you a picture that this shifts upwards and that shifts downwards. But there are no terms in that Hamiltonian that change the ground state or change the excited state. So what's my process to understand where this light shift comes from? What have I not yet done that needs to be done? I'm going to need to make another approximation. And there's only so many approximations you can make. So if you just start throwing out approximations, probably the first, second, or third one will be right. What was the second approximation you learned in quantum mechanics? Assuming the first was first order perturbation theory. It would probably be second order perturbation theory. So the spirit of second order perturbation theory is to imagine that you have a Hamiltonian with at least, let's say, a simple grouping of states like this and like this. So these are some ground states, which has an H ground. This is the Hamilton of excited state, it has HE, and there's some H ground excited that couples them together. And for this approximation to be valid, we're going to be wanting, oh, and there's a delta energy here. So there's also what I call over there. There's a typical energy splitting between this. It's large compared to those things, and it's large compared to that. When these criteria are satisfied, I can do second order perturbation theory. Do you guys remember the sort of generic prescription for that? So I'm going to generate a second order effective Hamiltonian from this. And as we write, we're going to have to define terms. So what I want to know is how the dynamics in the ground state are affected by the presence of the coupling to the excited state. But my goal is only to describe this in terms of the degrees of freedom present in the ground state. So this effective Hamiltonian has to act on the Hilbert space of the ground state. So I'm going to start with the projector operator. This projects onto the ground states. So ground is a sum over ground states, G, G. And we're going to have another one, Q, is 1 minus. Okay. So I'm going to project onto the ground states. I now have my ground excited Hamiltonian. I project on the excited states, Q. Actually, I have two Q's, but Q squared is 1. This is my projector onto the excited states. Okay. And what term have I skipped? What by dimensional analysis, what have I missed in this equation? Yeah, exactly. The energy I divide by is this EGE. So that's my second order effective Hamiltonian for the system. The interpretation of this is that you go from the ground state to the excited state, perhaps you evolve according to the excited state Hamiltonian for a while, then you come back down. In atomic physics, can you guys think of something that we very frequently think of in terms of this kind of description? Or if you have a condensed matter background, something that you think of in condensed matter that has this kind of description. So a condensed matter example is exchange interactions, effective magnetic interactions, where a particle might hop from one site, virtually sit there for a while, interact, and come back. And if you then project out the dynamics of double occupation using this kind of equation, you get effective, for example, magnetic interactions. A lot of magnetism in materials comes from that. In what we're about to do, what are we about to do? Why did I do this? What is my effective Hamiltonian? Oops, I relabeled it. Well, in our rotating wave approximation, This is HGE. So what's the interpretation of this process now? I have a far-off resonant laser. This is the first time I've used far-off resonant laser that virtually excites the atom to the excited state. It hangs around there for a little bit, acquiring a little bit of phase. The energy associated with EGE, which is in the denominator, and then I transfer back to the ground state. Right. So this is my second order term. And because I'm almost certainly falling a little bit behind schedule, if we plug everything into this, what are we going to get? We're going to get a factor of my coupling omega, two of them. It might be complex, although it's not in my example, omega squared. There's a factor of 4 because of that. There's a factor of the tuning in the denominator. And I believe I got everything. Let me check. Yes. Oh, I forgot one more thing. It's not an operator. So that's the shift. Let's do a quick sign check, because I think I forgot a minus sign here. So if it's as I drew it here, where my detuning variable is positive, corresponding to red detuned, we know that gets shifted down in energy, meaning I put a minus sign on. Okay, got a minus. All right, so this is it. We now are in position to understand optical lattices. Okay. Where are we? So first, what approximations are present for this to be an accurate description of the system? RF resonance. Yeah, so I need to say that my tuning needs to be large compared to my coupling. So the gap opened up in the spectrum is small. And actually, apropos to this, the very first question, requests for information said, what's wrong with the Bose-Hubbard Hamiltonian? And one response was, well, it's an open quantum system. So the tuning also needs to be much bigger than natural line width of the transition, which we haven't mentioned yet. So these are the sort of criteria that even just in order to have an optical lattice potential make any sense, we now need to be thinking about. To give a scale for this, though, it's actually relatively generous in the laboratory for these approximations to be valid. Generally speaking, in, let's say, in alkali atoms, for example, these Rabi frequencies are tens of megahertz to a gigahertz or something like that. We're quite intense beams, but we can easily detune by terahertz. So that is easily satisfied. And the natural line within that example is 6 megahertz. Other atoms might have 100 megahertz. Narrow line atoms might have a hertz. There's a wide range of transitions, but generally speaking, it's easy to satisfy these conditions. All right. So I want to come closer to reality now. Most of the time, for most transitions, what makes omega? What's it actually coming from? Like what physical process is making it? Yes, switch dipole. Yeah, that's right. So it's an electric dipole transition. So depending on your notation, it's going to look something like this. H for omega is going to be E, some dipole matrix element operator, dotted into the optical electric field. So I'm going to give you something that's sort of useful. So if we take that expression over there with this one, and we call this, I write it in a sort of implied summation notation, then we're going to get something that at least looks like this. I'm going to say that I have the scale factor of the term is still going to have a detuning kind of thing in the denominator. It's going to have, now I have EI, EJ, star, and then I'm going to put something in a box here. So my second order perturbation theory is described by, at most, a rank 2 tensor operator for my simple dipole transition. So I've done a couple things here because I want to be fast about this. I'm taking the complex conjugate of my electric field here, which means I've already transformed into a phasor rotation and thrown away the counter-rotating term. I should put hats on these. Okay, so I've done that, and I guess in that case the 4 is down there. Yeah, so it's a rank 2 tensor operator. And in a lot of systems, the fact that it's a tensor operator matters. For today, we're not going to concern ourselves with that anymore. This is just if you ever encounter these things, this is super common in real atoms. Okay, so just sort of keep that in mind. For the present case, though, of thinking about a 2-level atom, my 2-level atom has no structure. It's rotationally invariant, which tells me that if I break this up into irreducible tensor components, I have rank 0, 1, and 2 of those, only the rank 0 can matter, right? And the rank 0 component is something which is proportional to some constant. I'm just going to call this D0 squared times delta Ij. So for our 2-level atom, the only thing that can matter is something that takes the electric field times its complex conjugate. Delta, I lost some factors of E. I think I got, and the minus sign I forgot. So this is the kind of term that describes the strength of the AC Stark shift for a 2-level atom. And I made it unnecessarily complicated with this. Usually in a textbook, you wouldn't see rank 2 tensor operators. But they're so ubiquitous, I wanted to mention it. Okay, righto. So what does this tell you? This says that the strength of this potential is proportional to the square of the electric field, which is proportional to the optical intensity. So this is, I think, what you're probably used to thinking about. You have a lattice in optical intensity, and the atoms experience a potential proportional to that intensity, right? Are there any questions about any of this or comments? Remember the slide that the younger you are, the better your question is going to be. That's right. Yeah, so that's a super question. I'm going to answer it in 2 ways. So in the sense of open quantum system, I'm giving you a Hamiltonian description, meaning that usually you might want to describe this in terms of a Lindblad master equation. And if you do describe it in terms of a Lindblad master equation, there aren't losses per se. What's happening is you scatter photons into reservoir modes that you're not tracking, and that gives you the dissipation. The dissipation is saying that, well, microscopic reality is you're undergoing generalized Rabi oscillations, and this causes dephasing. It doesn't cause loss, though. The atom doesn't go anywhere. If you have to sort of add another layer on top of that, which is the photon recoil that might or might not cause the atom to be lost. In cold neutral atoms, typically loss processes are important. In ion traps, whose depths are tens of thousands of Kelvin, these spontaneous events don't cause loss. Yeah. Yeah, so let me repeat the question since no mic was up. So the question is, in this example, I'm coupling to one excited state mode. What if I couple to some other excited state mode and sneakily pick the phase of that coupling so the outgoing scattered light is actually would cause destructive interference between these two channels and thus suppress spontaneous scattering? The answer is yes. The tricky part is they have to make them degenerate, so you have to have the outgoing photons at the same frequency and the same mode so that when the environment measures them, it doesn't see very much. So one of my JQI colleagues is thinking about multi-photon ways of doing this in strontium, for example, where you have multiple pathways to two, angular momentum states of the same manifold that are degenerate. Yeah, so the question is, I'm going to rephrase it really, but how can this guy be optimized? And the truth of the matter is it depends on a lot of things that I haven't mentioned here, right? So for example, if all you wanted to do is make atom traps, no optical lattice or anything like that, then the turnaround question would be, how deep do you want these traps to be? Do you want them to be 100 microkelvin, a millikelvin, a Kelvin? And how small do you want them to be? The smallness is important because that's going to put a wavelength limit on it. If you want them really small, you're going to need short wavelengths and so forth. But if you have very, very generous requirements, many micrometers of trapping size, then my response is buy the biggest laser your budget can afford and make delta as big as possible. And there's, for experimentalists here, and in homage to the last talk, that usually means a CO2 laser. The CO2 laser optics are something you don't really want to deal with in one of our single investigator experiments. So in practice, it means a 1064 fiber laser or a 1550 for alkalis. For like ytterbium, we a lot of times use a 532, which you can get cheap and high power. Yeah, so for this scalar light shift case, the optimum is just a tuning. For the rank 1 tensor, or the vector light shift, there are actually more distinct optima because that's coupling involves a second order coupling to the fine structure constant as well, the fine structure terms. Alrighty, so let me make sure there's no key things I've missed. All right. So what I was going to do now, and I'm going to omit, I'm just going to sort of outline it, is I was going to say this. Okay, so our aim is to make an optical lattice. Our intuition is we need a standing wave of light to do it via this. And the way we're going to do that is create two counterpropagating beams with some atoms there. We have the scalar light shift. All I require is the polarization of the two fields be the same so I can interfere and make a standing wave. I'm just going to call that optical field strength E. So now I have two counterpropagating beams. My strategy here is I'm going to say, well, where the atoms are, the thing that goes into this equation is the total electric field. So I'm going to sum these things up. I'm going to magnitude square them, and I'm going to figure out what this term is like. And what you're going to arrive at is something that in the end looks like this. It's going to be a depth divided by 2, U over 2, plus U over 2. And I didn't probably write this too small. The K that's here is supposed to be a recoil, 2 pi over lambda. So what's the physical interpretation of this KR? So it's the recoil, well, wave vector. Now it's the recoil momentum. Right, so this is just the momentum of a single photon of wavelength, okay? And it also therefore is interpreted as the amount of momentum an atom would acquire if it were to spontaneously scatter one of those photons. So we've now made a lattice whose period is lambda over 2. And there's an offset term which we can forget about. So in terms of physical interpretations, actually we haven't made any more approximations here. We've done good. But how do we physically interpret this? Like, why is there a lattice present? What's the atomic physics way of thinking about it, and I insist that you use the word photon. So if you must use the word photon, what is this lattice doing? You think about the second order perturbation theory description over there. What's this lattice doing in terms of photons? Well, it's interfering, but could you get some additional words to go with that motion? It is making a standing wave, but I want to think about the second order process over there involving transitions and photons. So yeah, so I'm wanting your answer to involve the word photon and somehow the picture over there. So imagine our two lasers are containing an enormous flux of photons that are counterpropagating. What this atom is doing in a process sense is it's sitting there in the ground state. It's grabbing a photon from one beam. And once it does that and goes virtually to the excited state, it can do two things. It can choose to throw that photon back into the original beam. That gives you the U/2 term here, the overall energy and overall energy shift, or it can throw it into the other beam. If it throws it into the other beam, the atom that, let's say, was at rest needs to have acquired 2 photon recoils of momentum. It's going to be moving with 2 recoils of momentum. So with that, how is that information encoded in this term? Can anyone sort of, given my bad handwriting, it's more of a challenge than it needs to be. But yes, great. So I'll do that. So I have each of these are K recoils. I'll divide by 2. And then the important thing, I'll put hats here. I'll put my factors at 2. All right. So the first time in this talk, we're now thinking about spatial motion as also being a quantum degree of freedom. And exactly right, we decompose this into the sum of the 2 exponentials. But does anyone recognize that operator? Yes, exactly. And if you look at it, it shifts by 2 K recoil. So when I break my cosine into these 2 terms, it is exactly that thing which implements the momentum shift that intuitively we knew had to happen if you throw photons between beams. All right, great. So that's what our operator looks like. So I want to forget about the overall energy shift. And now I want to think about what the entire Hamiltonian looks like. So this is Hamiltonian for motion in the ground state, subject to the lattice potential. Right? So in terms of projectors onto the momentum states, my energy is h bar squared k squared over 2m. No trouble, right? And my lattice also sums up over all k states, but it goes from k to k plus 2k equal. I want you to notice that this is actually a momentum space exactly the same as the Bose-Hubbard Hamiltonian I wrote before, where in that case, in real space, you're hopping between lattice sites. Now in momentum space, you're hopping between momentum states. And then this is now having an overall energy. If we think about this in real space, it would be like having a harmonic trap-on, giving an energy in proportion to position for my Bose-Hubbard model. Now, there's no interaction here. There's no k squared term, I didn't second quantize. I don't have anything with 4 field operators. But in terms of the single particle physics, this is like tunneling. And finally, we're coming to the reason why I'm doing this right now before I do spin orbit coupling, because I want to give you a graphical way to think about this. So for those of you whose condensed matter class has happened and is fresh in your memory, the picture I'm going to draw right now is extremely familiar. But by doing this construction, I don't need to use Bloch's theorem or any kind of confusing stuff like that. I can do it pictographically. So what we want to think about is what are the solutions to this Hamiltonian? Incidentally, you guys have seen this Hamiltonian today in a very different form. So did any of you notice this Hamiltonian or perhaps with the cosine this morning? It's pretty obfuscated, so I'd be impressed if you know it, but anyone know what it is? Exactly, it's the Matthew equation. Right, so the solutions to this equation are exactly the same things that give you the stability diagram for atoms in ion traps. Yeah. Yeah, that's right. So that's right. There's no interactions present. So I'm good by using my projector operators in first quantization. So the way I want to think about this graphically, like this. My horizontal axis is K. I'm going to start by drawing the energy associated here with my kinetic energy. So I have a parabola like that. So this is now energy. And I'm going to define a new unit of energy for you as well. So the recoil. This is how much energy an atom that picks up a single recoil of momentum would have. Right. Alrighty. So what I want to think about is imagine that we're considering that state with some momentum K. And I want to understand what group of states that it's coupled to. Well, I look over at this Hamiltonian and say, well, it's coupled to, well, not itself, but some other state. Maybe my list is K plus 2K recoil. K recoil, 4K recoil, -2, -4, et cetera. And what I think about is, well, that state that I'm coupled to has some other kinetic energy. How much? Well, what I'll do is I'll draw a second parabola, spaced in energy by 2K recoil here, and track it up like this. But there'll be another one, 4K recoil, going up like this. There'll be another one at -2 here, going up like this, and so on. So I have an infinite family of parabola. And in condensed matter lingo, this is the extended zone scheme. Yeah. It's a second order, that's a second order process. Yeah, so I do need to include it because I think that the rigorously right way to think about it is this. If you wanted to make a matrix description of this, let's say to throw into a computer, or if you're clever enough to solve exactly, then I need to say what set of states are coupled together. And this is where this lattice intuition is super convenient. You can say, I have a lattice of points in momentum space that are coupled together. They're spaced by 2K recoil. And this grouping of things makes what's called something called the central matrix in band structure. And this is just a graphical thing that says, okay, I have an energy here, another one there, another one here, and this ladder of states going upwards. And those are simply the family of states to which that initial state is coupled. To avoid overcounting, you then define a Brouwer zone, which is inside here, which I'm not going to fill in because it'll make it impenetrable, but it runs from -1 recoil momentum to +1. And that's an artifact of these units. In condensed matter, usually it goes from minus the reciprocal lattice vector over 2 to plus reciprocal lattice vector over 2. And it's an artifact of me counting momenta in terms of photon recoils, a physical thing, rather than something to do with the band structure. All right. So make sure I haven't missed anything I wanted to say. Okay. So if we now turn on the lasers, just a little bit, so make omega, this diagram corresponds to the energies when omega is 0, what's going to happen? I'm going to redraw it because it kind of got cluttered there. Okay, So that's sort of the more minimal version. I turn on the laser just a little bit. What happens? In terms of the energy. So just like when you imagine in your head diagonalizing this Hamiltonian, what's going to happen qualitatively to this graph? Anyone? Yeah, so the first thing that happens qualitatively is every point there's a crossing, a little gap opens up. That's a first order gap. I go back over here, I say, well, I have something divided by, my matrix element divided by 4. So this is in fact, this will have a width of U naught over 4. So it's a kind of small sort of gap. U naught over 2, sorry. U naught over 2, my mistake. So then you open up a little gap in the spectrum. And now this thing becomes the lowest band that you would, that is just in which you're thinking about dynamics, for example, in our previously considered Bose-Hubbard model. No, there will. There'll be a really small gap here. But apropos to the question earlier, there is no direct transition between those two states. They're separated by 4K recoil. It's a second order transition. You go over to the second order equation, and we have to use that to estimate what that gap size is. And so forth. So for shallow lattices, we can compute analytically what happens everywhere, sort of by truncating to these 3 bands. It's a 3 by 3, and we can do some pretty good estimates with that. It's a lambda system, and there's some exact solutions in a lambda model. But the thing I wanted to take away from this is that the way to mentally organize your thoughts for this problem is in terms of these displaced parabolas. And if you want to know exactly what happened, you can look up the tabulated solutions for the Matthew equation, or Mathematica knows what it is. It's often just more convenient to write your own matrix solver. But in any case, that's what this is. Just to make a quick connection. So when you were thinking about the stability of an ion trap, what you saw in that graph were these sort of, I'm not going to draw it very well, but there were sort of regions of states like this that you saw sort of bending like that. Maybe you see some other ones going up. I think they went down, but this group of states here is exactly the same as the group of states in this lowest band. The narrowing here is a narrowing of the band as the lattice gets deep. So that's just interesting connection. Alrighty. And I think now, okay, now I need the projector back down. All right, so these slides, when they come back, it's just, oh, great. All right. So what we're going to think about tomorrow is an idea of spin-orbit coupling. And I'm importing spin-orbit coupling from condensed matter, which, when you look at these equations, looks like they have nothing to do with spin-orbit coupling at all in atoms, meaning there's no L coupling to a spin angular momentum. So what we have here is what's called Rashba spin-orbit coupling, and this is called Dresselhaus spin-orbit coupling, both for motion in a 2D plane. So this experiment from Joe Ornstein's group was looking at a 2D heterostructure, so a 2D electron gas, and it contained both the Rashba type and the Dresselhaus type spin-orbit coupling. And the thing I want you to look at is not so much the prefactors, alpha and beta are the strengths respectively, but what this does. This says that motion along the y direction couples to the Pauli matrix X. So as you move faster and faster, in fact, you start undergoing Rabi oscillations about the X direction in spin space. And if you go along X, around the Y direction and so forth, and these differ by which motion couples to which Pauli operator. Okay, so it's really spin linear momentum coupling or spin crystal momentum coupling. It does derive from the atomic spin-orbit coupling of the atoms building up this lattice, but it doesn't look like spin-orbit coupling. So what they did in this really cool experiment is they said, well, if we make alpha equal to beta, Rashba equal to Dresselhaus, you can sum them up and write it like this. So now I have the sum of 2 K vectors times the difference of 2 Pauli operators. By doing a rotation in spin space by 45 degrees and a rotation in real space by 45 degrees, we get a simpler form of spin-orbit coupling, actually a tip to Z as well, that couples X motion to the Z Pauli operator. Okay? So this is unidirectional spin-orbit coupling. And what they found in this paper is that exactly at this crossing point where these are equal to one another, the coherence time of a imprinted spin pattern was greatly increased. Okay, so that's sort of the result of this really cool paper, is the enhanced lifetime of a spin helix when imprinted in this point. Second reason, so that was really cool. I was reading these papers. In context, there was also a body of work going on thinking about topological quantum computation and the idea of Majorana fermions to implement this idea. And the group of Shankar Desarma at UMD was making proposals about how systems with spin-orbit coupling, along with S-wave superconducting pairing, could also realize these Majorana chains. So, and they have interesting stuff for 2D and 1D spin-orbit coupling. So in that context, we began to think about spin-orbit coupling, and I'm going to give you guys a homework problem. Now, the homework problem doesn't mean you have to actually do anything. What you should do is think, so that when you come in and I say, what does this mean tomorrow? You're ready with an answer that takes about 4 words. 4 words will be enough. So what we want to do is realize that Hamiltonian. So I want this Hamiltonian. So I want something that has a kinetic energy. It's independent of spin state. I want something that has a term that couples motion along one direction to the Z Pauli operator. And I want something that couples these 2 states together. That's the goal. How do we create this? And I didn't do the optical lattice stuff for nothing. So think about the context of the optical lattice and see if you can't just think about how you might construct this Hamiltonian. And you should think about the perturbation theory. What are the ingredients necessary? And you should think about, once you have those ingredients, how can you use light matter coupling? Obviously, we're going to have lasers involved in order to realize this. And then what I'll do is we'll talk through it, and then I'll give experimental examples of this and how we use this to make sort of accurate quantum simulations of Hamiltonians with spin-orbit coupling. So thanks, everyone. I think we're slightly late, but are there any further questions before I guess I'm done? Yeah. Oh, great. So let's see what we can. Okay, so the bit of the equation that I had is gone, but I'll just sort of redo it here. So we said that I can write it big over here. The perturbing part of the Hamiltonian, the part that the light creates, look like this. Okay, so I have my coupling, my lattice step divided by 4. And then I have a term that couples K to K plus 2K recoil. So this is why I sort of encourage you to think about this just as a lattice problem in momentum space. So what this says is that everything else being equal, if I have a degeneracy between K and K plus 2K recoil, which happens when K is minus 1K recoil, because then that's minus 1 and plus 1, and they have K squared is the same in that case. There's a crossing between those at that one point. Now I can approximate that in my head as a 2-level system. It's degenerate and is coupled by strength U naught over 4. So then I know it's going to open up a gap whose size is going to be U over 2. And that's sort of what I meant, is that in this weak coupling limit, I can make an approximation of a 2-level Hamiltonian there and have a good answer until such time that the 3rd and 4th and so forth levels become important. And another place in the center, I have a 3-level description with something at K naught and then 2 things at K plus or minus 4. So I have an effective 3-level description there.
I just wanted to ask that the unitary matrix which made this system time independent, the Hamiltonian, I identified a unitary matrix which made our system time independent. So can you comment on the existence of such unitary matrices for higher dimensional problems, like if there are more number of energy levels involved? So can we say that such kind of matrix always exists or not, or does it depends on the problem at our hand?
Okay, so I'm gonna say what I think the question was. So I think what you were asking is, under what circumstances can I follow this prescription of making rotating frame transformations and rotating wave approximations to land myself at a time-independent Hamiltonian? Yeah, so there is a sort of nice graphical picture you can use to determine whether or not this is going to work. So what you're aiming to happen is that when you make a series of rotating frame transformations, that you end up with a bunch of terms with zero frequency. That's what you want to happen. So let's just say that we have 3 levels. Like that, okay? And we wonder, when can we make this transformation? So let's start with something that's definitely the case. If I put one laser like that, I can absolutely make that transition because this one's decoupled. And I'll just imagine shifting this down and everything is good. If I make this laser, an additional laser like that, I can also do it. Because the energy difference between this state and this state matches that difference. When I try to subtract from this one and this one, I'm going to end up removing the frequencies. And if I close the loop, it's also going to work. In fact, that's the general answer. If I have a series of states and when I draw the photon energies, they always touch head to tail, then it's going to work. But if I, let's say, make this one miss like that, then no matter what I try to do, I'm going to have that amount of angular frequency left after I make these transformations. Okay, so the photon pathway, the laser photon paths have to make, if they have closed loops, they need to close. So if I have zigzag chains, I can make a chain as long as I want, it's going to work. But as soon as I try to couple states together in a ring, I need to make them touch head to tail. And if you don't do that, then after you do the rotating frame transformation is exact. But you're going to have to describe the problem with Floquet. So you're going to have a series of one or more frequencies left behind, and then you need to do the Floquet problem your favorite way at that point.
Are there any further questions? Short questions, maybe? Short questions?
It's just related to that. So, so if you have 3-level system, then we have to have this at least 3 lasers like this.
No. Like it's super common in the lab, for example. This is like a really iconic level scheme. G1, G2, and excited. This is called the lambda scheme, and it's what underpins like the idea of EIT if you throw in dissipation, or you have a dark state in this one. So there's what's a STRAP is a process by which you can have adiabatic transfer. So this lambda scheme is super well studied. You don't need to couple those together, but you could. If these are 2 ground states, they're probably a microwave photon apart. So you could have a microwave oscillating magnetic field that couples them together. If you're using like strontium, you can have multiple excited state transitions. So you have lots of choices.
Okay.
Okay, I don't see any other questions. So let's thank the speaker and